So in this video I am going to talk about a method of root finding, and that method is known as Newton-Raphson method. Usually this method is used to improve results obtained from other methods like bisection, etc. Now let us consider that we have a function and x0 is an approximate root. Let us consider that x1 is the exact root of the function. It means that f at x1 is equal to 0. And also let us consider that x1 differs from approximate root by a small amount h. Here h is small. So now I can write down this equation 1 as f at x0 plus h equal to 0. Now using Taylor's series, I expand this function about x equal to x0. So I can write down it as f at x0 plus h derivative of f at x0 plus h square by factorial 2, second derivative of f at x0 plus h cube by factorial 3, third derivative of the function at x0, and so on and so forth. Now because I am considering h is small, so all higher order h values will have negligible effect on the series, therefore I can neglect them. So neglecting this, I get only first two terms, f at x0 and h into the derivative of f at x0 equal to 0, and from this I obtain that h is equal to minus f at x0 divided by derivative of f at x0. This is equation number 5. Now if I substitute equation 5 for h in equation 2, I get x1 is equal to x0 minus f at x0 divided by derivative of function at x0. So this is my approximation x1. Then I can find out similarly next approximation and so on. So the n plus 1th approximation will be xn minus f at xn divided by derivative of f at xn, and this is Newton-Raphson formula. Now if we see that in fixed point iteration method the fixed point iteration method operates like this. So if I consider that g at xn is equal to xn minus f at xn by derivative of it at xn, then equation 6 becomes equation 7. In other words, it is nothing but fixed point iteration method. So it means that Newton-Raphson formula is a special case of fixed point iteration method. Now, what is the convergence condition in case of Newton-Raphson method? So let us say that alpha is the root of the function, that is at alpha this function is equal to 0. So for convergence the following conditions must be satisfied. That number 1, the derivative of f should not be equal to 0 for all values of x in a given interval, and that interval is alpha minus delta to alpha plus delta, where alpha is the root. Second is that second derivative of x is continuous for all x in the given interval. And next is that the multiple of f and the double derivative of f should be less than square of the first derivative of the function. So the successive approximations will converge to the root if we start with initial approximation close to the root. So now how we have got this third condition, this is what we are going to see. So for that, let us look at fixed point iteration method, that how it operates. So, and the Newton-Raphson formula or Newton-Raphson method operates via this formula. So it means that g is equal to x minus f at x by derivative of f at x. And if I take the derivative of g, then it comes out to be f at x into double derivative of f at x divided by square of first derivative of f. And because we know for successive operations, successive approximations to converge, the absolute value of derivative of g should be less than 1 in case of fixed point iteration method. So therefore from this we find out that f at x multiplied by double derivative of x should be less than square of first derivative of the function. Now we have seen analytically that how we can derive formula for Newton-Raphson method. But then what this geometrically mean? So we are going to see geometrical meaning or geometrical interpretation of Newton-Raphson method. So for that, let me consider that there is a function and this function is something like this. So this method says that if I choose some initial approximation x naught and from there I draw a tangent, this is a tangent which is at point x naught on the curve, then wherever this point will intersect this x-axis, that is your next approximation. And so then this part of the curve we will omit and next tangent will be drawn from here, and from that we can find out the next approximation, and this way if we continue then we can reach to the root. Now if the curve is steep, then we shall be able to obtain root quickly. On the other hand, if this function is nearly parallel to this x-axis, then the convergence to the root will be very slow. Now as we have discussed theory of Newton-Raphson method, now let us see that how does it work with an example. So let me consider an equation x square plus 9x minus 8 is equal to 0. Now let me consider the function is x square plus 9x minus 8. So first of all I need to obtain an interval in which the root lies. So if I substitute x equal to 0, I'll get 0 plus 0 minus 8, that is minus 8, and this is negative. And at x equal to 1, the value will be positive. So from here I can see that root lies between 0 and 1. So 0 and 1 is the interval within which the root lies. Now I have plotted this function and we can see that it has two roots. One root is over here and another root is over here. Now how to find out root using Newton-Raphson method? So let us write down the formula for Newton-Raphson method. Xn plus 1 is equal to xn minus f at xn by f prime at xn, and f prime is derivative of function at xn. Now in order to start the iteration, let us approximate that initial value is 0. So it means x1 will be x0 minus f at x0 divided by derivative of f at x0. And if I need to find out function at x0, that is f at 0, this is minus 8, and the derivative of function is 2x plus 9, so its value at 0 is 9. So using this, x1 will come out to be equal to 0 minus 8 by 9, or my first approximation is 0.888 9. Once I got the first approximation, I can obtain the next approximation. So the second approximation will be given by 0.8889, and the value of function 8.889 is 0.7902, and the value of derivative of the function at 0.8889 is 10.7778. And so if I substitute this 0.7902 divided by 10.7778, and using this I find out the next approximation to be 0.8156. Now if I calculate the same way, the third approximation will be 0.8151. What do we see over here? That up to third decimal places, this is same, these values are same, so therefore the root correct to 3 decimal places is 0.815. Now we have seen that how in practical applications we can apply Newton-Raphson method to find out the root of the given equation or given function. Now we are going to see that how the errors decrease in this case, that is in the case of Newton-Raphson method, or in other words, that how the root converges. So for that, let us consider alpha is the root. So it means that f at alpha is equal to 0, and let us say that xn is nth approximation. Now using Taylor series expand the function about xn. So we get f at xn plus alpha minus xn into the first derivative at xn plus alpha minus xn square by 2 second derivative of function at xn, and so forth is equal to 0. Now neglecting higher order values, so what we get? We get f at xn divided by derivative of f at xn is equal to alpha minus xn plus 1 by 2 alpha minus xn square f double prime xn divided by f prime at xn. And this is nothing but we can write down from the Newton's formula that xn minus f at xn by f prime at xn is equal to xn plus 1. So using this I can write down xn plus 1 minus alpha is equal to 1 by 2 alpha minus xn square f double prime at xn f prime at xn, and this is nothing but the error in n plus 1th approximation. This I can write down it like this also, xn minus alpha. So, and this is nothing but error in nth approximation. So what I find out that n plus 1th error is equal to square of error in nth approximation. In other words, the convergence to the root is quadratic in nature. So if I start with the initial approximation close to the root, then the successive approximations will converge very fast, very quickly as compared to the fixed point iteration method, because there the convergence to the root was linear. Here convergence to the root is quadratic or second order. Now we can find, using this method, complex roots also. Now in order to understand this, let us consider an equation x square plus 2x plus 9 equal to 0. As we know, its roots will be minus 1 plus minus 2.828i, where I is square root of minus 1. Let us say that we do not know anything about its root. Let us pretend it that we do not know anything about the root of this given equation. Now if I plot this equation, then this equation will look something like this. And as we can see over here, that this plot does not intersect x-axis anywhere. It means that it contains imaginary root. The root is complex in nature. So in order to solve this problem, let me write down f at x is x square plus 2x plus 9, and for finding the complex roots we have to start with the initial approximation complex. So if we start with the initial approximation or complex approximation, then the root which we are going to find out, that will also be complex in nature. Now the derivative of this function is 2x plus 2. So the functional value at x naught, if I solve it, 1 plus I whole square plus 2 into 1 plus I plus 9. So this comes out to be equal to 11 plus 4I. And similarly, the derivative of this function will be equal to 4 plus 2I. And so the first approximation will be 1 plus I minus 11 plus 4I by 4 plus 2I, and to rationalize this denominator, I multiply it with its complex conjugate, and so from here if I solve, I will get it equal to minus 1.6 plus 1.3I. Now using the same method, now this will be the approximation to find out the next approximation, and the next approximation is x2. So using this, substituting this in Newton's formula or Newton-Raphson formula, we get the second approximation to be 0.206 plus 1.566I. Similarly, x3 will be minus 2.080 plus 2.387I. x4 will be minus 0.917 plus 2.587I. x5 will be minus 1.008 plus 2.838I. x6 will be minus 1 plus 2.837I. x7 is equal to minus 1 plus 2.828I, and x8 will be equal to minus 1 plus 2.828I. And as we see that the 7th and 8th approximations are same up to third decimal place, so the root correct to 3 decimal places is minus 1 plus 2.828I. This is what the one of the complex root will be. Another complex root is its complex conjugate, and in order to obtain that, we can start with the initial approximation x not equal to 1 minus I. Why we have chosen 1 minus I? Because it is complex conjugate of 1 plus I. So therefore, if I start with this initial approximation, I shall be able to find out its complex conjugate of this, and that will be another root of the given equation. Now using Newton-Raphson method, we can find out root for algebraic equation, we can find out root for transcendental equation, also we can obtain complex roots the way we have obtained in the above example. Hope you would have understood Newton-Raphson method properly.